Hello everybody, good afternoon. Welcome to the lecture series of Analog Electronics. My name is Lecture1, Assistant Professor of ECE Department, G. Polarity Engineering College. Analog Electronics having more number of applications in our daily life. If you want to design an effective communication system, Analog Electronics is playing an important role. In that, amplifiers are playing a very crucial role for an effective communication system. Like in transmitter, we require the amplifiers, in receiver, we require the amplifiers. For example, if you want to have an effective communication system, before transmitting the signal at transmitter side, we used to have the pre-emphasis is a process that will amplify the signal. Why? Because as signal undergoes through the channel, it experiences decreasing of the amplitude, the signal will be degraded. And obviously at the time of reception, once again we will try to amplify the signal and we will do further process. Let me run quickly about the contents of our discussion. First, initially I want to concentrate what is faithful amplification, and after that I want to highlight that in order to achieve this faithful amplification, what are the important considerations we have to make with respect to DC analysis as well as with respect to AC analysis. Next, I want to concentrate operating point, and at the same time, in order to locate this operating point, we require the DC load line. And after that, I will come across through transistor biasing stabilization circuits, in which what are the best circuit and how many types are there, and how we will decide that which circuit is stable. Before going to discuss about all this analysis, first I want to make a basic consideration of why we require the amplifiers. Without amplifiers, we can't amplify the signal, we can't increase the strength of the signal. According to the definition, an amplifier which increases or boosting the strength of the signal. Strength of the signal is known as amplifier. An amplifier is an electronic circuit which increases the or boosts the amplitude of the signal or strength of the signal or intensity of the signal is known as amplifier. For example, we consider it is an amplifier and I am applying a weak signal. In order to increase the strength of the signal, I have to give as an input to an amplifier and I am achieving an amplified output. This amplified output is known as faithful amplification. The main aim of an amplifier is I have to make it the output must be faithful amplification. What is faithful amplification? Faithful amplification means throughout the cycle, the signal have to be amplified by the amplifier. For example, in this case, the input signal what I am applying is having the cycle of 0 to 2 pi. One complete cycle is varying from 0 to 2 pi. I have to amplify 0 to 2 pi. In the output, you can observe that the positive cycle is amplified as well as the negative cycle is amplified. This is known as faithful amplification. Only some portion of the input signal is amplified and the remaining portion is not amplified. It is not faithful amplification. So practically, if you are using any amplifier in any communication system, we have to see that the main aim of the designing the amplifier is I have to achieve faithful amplification. If I am not getting faithful amplification means I have to modify the circuit. I have to go through that, what are the drawbacks which are going in my design, and I have to modify that and I have to achieve faithful amplification. After that, we have to make how stable the output is. The two main aims of designing the amplifier is one is faithful amplification and another one is stability. Stability is one of the important parameter what we have to consider. After getting the output from the amplifier, how much stable the output must be. So today I want to concentrate on faithful amplification as well as some of the topics which are related with the stability. So next I will consider that in order to achieve the faithful amplification, what are the steps we have to follow. So first one is zero signal collector current. The first consideration what we have to consider, zero signal collector current. We will discuss in detail about this later. First, I will try to highlight that what are the important points we have to consider in order to achieve faithful amplification. The first one is zero signal collector current. The next one is minimum VBE or minimum input bias what we have to apply at any instant. Minimum VBE at any instant. Next one is minimum VCE. How much output bias we have to apply and how much output bias we have to maintain in order to achieve the faithful amplification. These are the three steps what we have to consider in order to maintain the faithful amplification. I think already we know that we are using the transistors, MOSFETs, FETs as well as CMOS or some of the active elements inside the amplifier. In order to design the amplifier, we can use either BJT, either FET, either MOSFET or some of the developments whatever which we are coming across on the MOSFET. Currently, I want to concentrate how can we design the amplifier by using BJT. In that BJT, it consisting of 3 terminals. For time being, I am considering only CE configuration. CE configuration is one of the best configuration that already we know that from EDC. Why? Because we can maintain high voltage and high currents compared with CB as well as CC. In CB configuration, voltage gain is high but current gain is minimum. In CB configuration, voltage gain is maximum, voltage gain is high, whereas current gain is minimum. Whereas in CC configuration, voltage gain is minimum and current gain is maximum. Whereas in CE configuration, voltage gain is high as well as current gain is also high. That is the advantage what we are considering if you want to design any amplifier rather than preferring common base configuration or common collector configuration. We used to prefer majorly common emitter configuration only. So for time being, if I want to design any amplifier, I am considering CE configuration only. That is the reason why I am telling VBE as well as VC. These 3 points is not only applicable for CE configuration, even applicable for CB as well as CC also. Anyway, first I want to concentrate these 3 points in order to achieve faithful amplification. That first one, zero signal collector current. What is the meaning of zero signal collector current? And how can we get the signal? How can we get the output without applying a signal? So the most important thing is, if you want to work out an amplifier effectively, we require the 2 supplies. One is a DC supply, where in order to have the biasing, after giving the proper biasing to the amplifier, then I want to run the application by applying a weak signal as an input to this amplifier. Then only I am getting an amplified output across the CRO or whatever the output meter what we are considering. For example, you carefully observe that this is the AC signal and this is the DC supply. So zero signal collector current means without applying any AC signal, I am applying only DC supply only. Whatever the current I am getting, that I am considering as IC. Here one thing, before going to discuss in detail about the analysis of these amplifiers, first I want to concentrate that the DC currents and DC voltages are represented by using capital letters. For example, you consider the collector current only DC supply I am applying means this is DC current only. If I apply AC signal, I am getting the output as, we have to represent in small letters. This will represent only AC signal representation. AC signal only, and this will represent DC signal only. Only DC I am representing everything. Capital letters, even suffix also we have to represent in capital letters only. That is a notation of DC representation. For AC representations, notation, it is represented in small letters, and its suffix also we have to represent in small letters. That is AC. In the combination of AC plus DC, the main notation we have to represent with respect to small letter, and the suffix we have to represent with respect to capital letters. This will give the combination of AC plus DC. Nothing but the main letter representing the AC representation, and the suffix letter will represent the DC representation. Anyway, this is the analysis what we are considering in order to understand the notations. Here, zero signal collector current means only I am applying the DC supply. That is the input what I am giving to this amplifier. According to that, I am getting only DC output. Whatever the value I am getting the DC output, that is IC. For example, if I am applying only AC signal, now I am applying only AC signal rather than DC signal, I am getting the output as small IC. So according to the definition of zero signal collector current, in the sense, whatever the output we are getting with respect to only DC supply IC must be greater than the output of whatever we are achieving only AC signal is applied. Zero signal collector current means the collector current whatever we are applying, whatever we are achieving without applying any AC signal, that current must be always greater than equal to the current whatever we are applying the AC signal. That is the meaning of zero signal collector current. And the next one is minimum VBE at any instant. Minimum VBE at any instant. Just now I explained that. I am giving an explanation regarding that. I am using only CE configuration. For example, now I am connecting a transistor which is in CE configuration, and I am considering NPN transistor. I am considering NPN transistor. NPN transistor where this is emitter, base and collector. So input I am applying the forward bias. So P is connected to the positive terminal of the battery and N is connected to the negative terminal of the battery. Similarly, output I am applying the reverse bias. N is connected to the positive terminal and N is connected to the negative terminal. If you carefully observe that this is positive and negative, positive and negative. Input is forward bias and output is reverse bias. I am connecting the voltage supply VBE in between base and emitter. I am connecting the voltage supply VCE in between collector and emitter, where emitter is common. Why it is called the common emitter? Emitter is commonly useful at the input side as well as at the output side, so that it is called common emitter configuration. The input voltage whatever we are applying, that must be greater than 0.7 if it is a silicon type of transistor. That is the minimum voltage what we have to consider, and it must be 0.3 for germanium. That is the condition what we have to consider. That is the meaning of minimum VBE at any instant. At any instant, if you consider that, the input voltage always we have to see that must be greater than 0.7 for silicon and 0.3 for germanium. The next one, similarly, the next condition is minimum VCE at any instant. So I am trying to show the two conditions in a common diagram. What is the minimum voltage we have to maintain at the output side? What is the minimum voltage we can supply to the transistor at the output side at any instant? That is a VCE must be greater than 0.5 for germanium and greater than 1 volt for silicon. So it is volts only. 0.5 for germanium as well as 1 volt for silicon. That is the output biased voltage what we have to apply in order to get a faithful amplification. So finally what I want to conclude that to achieve the faithful amplification, we require the proper biasing at the input side as well as output side. In order to achieve this proper biasing, we have to, what is the meaning of biasing? that already we are having a prerequisites of EDC. Biasing is nothing but giving voltage supply or giving external supply. So if you want to use the transistor inside the amplifier, means we have to give the proper biasing. In order to find the effect of biasing on the transistor characteristics, if I want to find the effect of biasing after giving the biasing and how much effect we can observe on the transistor characteristics, or I want to find out that on which region the transistor is operating after applying the biasing, for that purpose we require the knowledge of operating point and DC load line. So I want to concentrate DC operating point or commonly called as operating point, another name as Q point, another name as quiescent point, all will give the same meaning only. So this knowledge is required as an engineer in order to design an effective amplifier. Without the knowledge of operating point, we can't find out that on which region transistor is operating. But in order to locate this operating point, we have to link up with one more consideration known as DC load line. In order to locate this operating point, I required some DC load line. Operating point will defines or will explains that on which region the transistor is operating. But in order to locate this operating point, we require the knowledge of DC load line. Both are interrelated. So before going to discuss in detail about the how we have to locate the operating point and how can we find out that on which region the transistor is operating and how can we locate the operating point on the DC load line, what is the importance of the DC load line, and with the knowledge of DC load line, what are the final characteristics what we are achieving, what parameters we can find out, all these things we will try to come up after having a basic analysis or some of the elementary concept of CE configuration and its characteristics. Anyway, now I want to concentrate on, in order to understand the operating point, now I want to concentrate on CE configuration output characteristics. That already we are familiar with CE configuration output characteristics. For example, this is a transistor, emitter, base and collector. The transistor what I am considering as NPN. According to the knowledge of faithful amplification, we concluded that input must be forward bias, output must be reverse bias, so that this is VBE, this is VCE. Here we are getting the input characteristics and here we are achieving the output characteristics. So currently I want to concentrate the output characteristics. To find out the output current, I require the AEC. To find out the output voltage, I require the knowledge of VCE. To find out the input current, I require the knowledge of IBE. To find out the input voltage, I require the knowledge of VBE. So output characteristics I am drawing in between output current as well as output voltage. By controlling the input current, that already we proved in the EDC, transistor is a current control device. Transistor is an current control device. What is the meaning of transistor is a current control device? In the sense, input current is controlling the output current. Why? Because the output current is not depending upon the output voltage. The output current, I am repeating once again, the output current is not depending upon the output voltage. The output current of a transistor is depending upon the input current. That's why it is called the current control device. This already we are coming across some of the elementary concepts of CE configuration in EDC. Anyway, now I am trying to draw the output characteristics of transistor. This is also one of the example we can prove that how the output current of a transistor is depending upon the input current. Here I am trying to increase the IB current from 50 microamperes to 100 microamperes. Obviously the collector current will increases from as IB increases. Now you carefully observe that IB is 50 microamperes. I am trying to shift the IB from 50 to 100. Obviously collector current is also increases certain value compared with the previous value. Still, if you try to increase this to 150 microamperes, still we can observe that some more current is increasing at the output side. With this example, we can easily conclude that the input current is controlling the output current. Anyway, finally, after plotting the output characteristics of a transistor, I am trying to highlight the three regions. This is the region initially where the current is increasing. After reaching certain point, it will be saturated and we are getting the constant IB. The region where current is constant, this region is known as active region. Active region. So before going to discussion of an operating point, I want to come across some of the elementary concepts of CE configuration. In that process, I am trying to highlight here. Here we are achieving the linear region where the current is increasing along with the voltage. This region is known as saturation region. Saturation region. And once again here we are getting very low current and this region is known as cutoff region. So finally, from the output characteristics of a transistor, we are trying to highlight the three important regions. One is active region, another one is saturation region, another one is cutoff region. If I want to move the transistor to active region, how much biasing I have to apply? That is the question. If I want to move the transistor into the saturation region, how much biasing I have to apply at the input side and the output side? If I want to move the transistor to cutoff region, how much biasing I have to apply at the input side and output side? That already we know that if I want to move the transistor and I have to work out any application in the active region particularly, input must be forward bias and the output must be reverse bias. That is a condition what I have to consider. If I want to move the transistor into the active region, input must be forward bias and output must be reverse bias. Then it can be used as an application as, if I use this condition, I can use the application as amplifier. That is a major consideration what we have to calculate or what we have to analyze from the characteristics of a transistor. Similarly, if I want to move the transistor into the saturation region, I have to use input must be forward bias, output must be also forward bias, then I can use as on switch. Similarly, if I want to move the transistor into the cutoff region, or I want input must be reverse bias and output also reverse bias. So this is a condition what we have to consider, so it can be used as off switch. By locating the operating point, we can easily identify that on which region the transistor is operating. That is the main intention of that. After giving the biasing, what changes we can observe on the transistor behavior, that can be determined by using the operating point. Generally, operating point or a quiescent point is useful in order to identify the on which region the transistor is operating. But it's very difficult for us to locate the operating point directly. That's why we require the DC load line. DC load line will explains the maximum current and maximum voltage that can withstand by the transistor. Okay, so finally, the operating point is nothing but to find the effect of biasing, on transistor characteristics, To find the effect of biasing on transistor characteristics, we required an operating point. We required an Q point. That is one way of representing, or to find the on which region transistor is operating. To find on which region transistor is operating. Also, we use the operating point. Operating point is nothing but finding the output current and output voltage. For example, just now I considered the output characteristics of a transistor. Here we used to concentrate how can we locate the operating point. That is a concept. Just now I defined the output characteristics. We are taking the output characteristics in between IC as well as VCE, and these are the characteristics. For example, if the operating point is existing at this point, indirectly we know that the transistor is operated in active region. Or if the operating point on this region, we know that the transistor is operated at saturation region. Or if the operating point is existing on cutoff region, of course, in this area, we can easily identify the transistor is in cutoff region. But to locate this operating point, we require the DC load line. For example, this is IC, this is VCE, this is a DC load line, which will give DC load line will explains the here also output current, a maximum output current and maximum output voltage. That is called the DC load line. Why? Because unless you locate the DC load line, it is not possible for us to locate the operating point. So before discussing about the operating point, first we will try to concentrate on DC load line. DC load line will explains the what is the maximum current getting from the transistor and what will be the maximum voltage across the transistor. The maximum limits of currents as well as voltage that can be defined by using DC load line. For that I am considering a small example. In all this analysis I am taking a common concept as CE configuration only. Viewers have to be identify that in every explanation of each topic of which are related to the amplifiers, in this lecture 1, I am trying to concentrate as CE configuration only. Okay friends, so now we will try to consider, this is the transistor, this is VCC, and this is RC, and this is IC. Of course, this is RE, and which will be having the bypass capacitor, which is grounded. I am trying to highlight the outer section of the transistor, and this is VCE. So I am trying to highlight only the outer section of the transistor. Now a KVL is applied to this path by applying the KVL. Applying KVL to path 1. So the total VCC is equal to ICRC plus VC. Okay. Now if you carefully observe that, here I want to locate the maximum current from the diagram. I required IC maximum. What is the condition for IC maximum? When VCE is equal to 0, I am getting this maximum value. Similarly, if I want VCE maximum voltage of the transistor, what is the condition? When IC is equal to 0. On this axis IC 0 only, we can locate the maximum voltage. On this axis, if VCE 0 only, we can locate the maximum current. That is the condition what we have to consider. Okay. So for VCE maximum, you consider this is equation 1. For VCE maximum, if I want to find VCE maximum, I have to take the condition IC must be 0. So this is equation 2. Apply 2 in 1, so that we are getting as VCC is equal to IC is equal to 0 into RC plus I have to consider VCE maximum is equal to VCE. Why? Because when IC is equal to 0 only, we can achieve the maximum voltage. So according to this condition, VCE maximum. So that VCE maximum voltage is nothing but how much voltage we are applying, then only we are getting the maximum voltage. This is equation 3. So we are locating the DC load line by for taking the condition as IC is equal to 0 and finding the maximum current. Similarly, I have to locate the maximum current by taking the condition as VC is equal to 0. So we have to find the IC maximum when VC is equal to 0. So apply VC is equal to 0 in 1. Consider IC is equal to IC maximum. This is the condition what we have to consider and apply in equation 1. By applying these initial values on equation 1, so that I am getting as IC maximum is equal to VCC by RC. That is a maximum value what I am achieving. So according to the diagram, I am trying to first initially locate the IC maximum as well as VCE maximum. Without finding the DC load line, it is not possible to find out that on which region the transistor is operating. So this small analysis will explain that to locate the DC load line. DC load line indirectly explaining that what will be the maximum current getting from the transistor and what will be the maximum voltage achieving from the transistor. After locating the DC load line, the next content what we have to concentrate on, operating point. So once again I am trying to draw the same DC load line from the output characteristics of a transistor. This is IC, this is VCE. So I am trying to locate the DC load line. This is VCE maximum, this is the maximum voltage, and this is IC maximum and maximum current. This already we defined as VCC by RC, the maximum voltage, that is VCC. For example, if the operating point is existing at the center of the DC load line, operating point is nothing but Q point. You consider if the operating point is existing at the center of the DC load line. So how can we locate the operating point? Indirectly, what is the meaning of an operating point? Indirectly, I am locating the IC as well as VCE. Q point is explaining what is the output current and what is the output voltage of a transistor. DC load line is also output current and output voltage of a transistor, but its maximum value. There is a lot of difference between the DC load line as well as operating point. This is DC load line. DC load line will give the information about that what is the maximum output current as well as maximum output voltage. But the Q point is giving the information what is the current across the transistor and what will be the voltage across the transistor at that moment. For example, you consider this Q point is existing at the center of the DC load line, then it is, that is, transistor is operating in active region, so that we will achieve a faithful amplification or the complete cycle is amplified. So from this example, I can represent that the transistor is operating in active region. The most important thing is, after locating the operating point, we have to consider if the Q point is center of the DC load line. Center of the DC load line. The meaning of that, it is operated in active region. That is the first condition. So that is the advantage of locating the Q point. The next one, if the Q point is lying near VCE maximum, This is IC maximum. This is IC. If the Q point is lying near VCE maximum, then obviously the transistor is operated in cutoff region. If the Q point is lying near VCE maximum, if the transistor is operated in cutoff region. If the transistor is operated in cutoff region means indirectly the complete cycle is not amplified. By seeing the diagram, this is clipped off. This is clipped off. Meaning of that, this portion is not amplified. So if a transistor is operating in cutoff region means we can't achieve the faithful amplification. So we have to see that always the transistor must be in active region. Similarly, if the transistor is operated in saturation region, also we are getting a clipped off. If the Q point is lies in the saturation region or near ICE maximum, if the Q point is in the saturation region, also we are not achieving the faithful amplification. From this example, we can easily define that this portion is clipped off. We are not achieving the faithful amplification. If the Q point is not getting, once again, this portion is clipped off. So from this analysis, we conclude that locating an operating point is an important task. If the operating point is existing at the center of the DC load line, then we can use it as a faithful amplification. Nothing but indirectly, the transistor is operated in active region. So once you locate the operating point, then only we can find out that on which region is the transistor is operating. Locating the operating point itself, the work is not completed. How much stable the operating point is there? Why? Because transistor is influencing number of parameters. Amplifier indirectly influencing number of parameters. Due to implicit parameters or explicit parameters, there will be chance of varying of output current and output voltage. Means as internally inside that overheat is generated inside the internal components, IC current will changes. For example, you consider transistor is located at the center of the DC load line. At this instant, you consider transistor is located at the center of the DC load line and we are getting the perfect output and true amplification is taking place. Nothing but faithful amplification is coming. But unfortunately, due to variation of internal parameters or explicit parameters, suddenly there will be a chance of having the temperature rising, the surrounding environment of an amplifier. As temperature increases, BJT is a bipolar junction transistor where the output current is depending upon the output current of a transistor is depending upon the majority carriers as well as minority carriers. So temperature increases, obviously ICEO increases and that will vary the IC current. As IC current varies, obviously the operating point is trying to shift. Then it will be trying to go from active region to saturation region or active region to cutoff region. Then obviously we can't achieve the true amplification or faithful amplification. So finally, the bottom line, locating the operating point or estimating on which region the transistor is operating is very important. At the same time, the stability of the operating point is also very important. Even the explicit parameters or external parameter is influencing on the transistor. Internal parameters are influencing on the transistor. Also, we have to maintain the constant output current as well as constant output voltage. For that purpose, we require the transistor biasing stabilization circuits. Giving biasing to an amplifier is not completed. Giving a proper biasing to the transistor which can be used as an amplifier, our job is not completed. How much stable the output is maintained, how much stable the output we are getting, how much stable the transistor is working, how much stable the transistor in the active region. Throughout the lifetime, I have to get the faithful amplification. Once I design the amplifier, if I am using in a practical application, throughout the application, I have to see that whether I have to get the faithful amplification or not. At this moment, I am getting the faithful amplification. At the next moment, I am not getting the faithful amplification, means it is not the proper designing. That's why I have to see that whenever I used to run the application from the amplifiers, I have to get the faithful amplification. For that purpose, I have to keep the operating point at the center of the DC load line. The operating point should not deviate from the active region to some other region. For that purpose, I require the transistor biasing stabilization circuits. With this, I want to conclude here. In the next lecture, I want to explain about the different topics of stabilization circuits. Among this, which one is the best circuit, and how can we define this circuit by using a parameter known as stabilization factor. Thank you.